Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Sabee Grewal, who will tell us about nearly time-optimal pure state tomography with Pauli measurements. Sabee is a PhD student at the University of Texas, Austin, advised by Scott Aronson, and a student researcher at Google Quantum AI. He's interested in quantum algorithms, quantum learning theory, and quantum complexity theory. So Sabee, the floor is yours.
Awesome. Thanks, Jello, for the introduction. Thank you all for having me. Yeah, I'm going to tell you about this recent paper called Nearly Time Optimal Pure State Tomography with Pauli Measurements. This is joint work with Megal, William, Anirudh, and Mahir. So to start off, I wanted to make sure we're all on the same page and just tell you about the problem we're going to be thinking about for this talk. It's the quantum state tomography problem. So uh, the setup is that we've written some code on a quantum device, or we have some experimental apparatus or something, just some black box process where we can press a button and it will produce some unknown quantum state for us, some unknown state rho. And you can think of this as a collection of a bunch of qubits, or you can think of this as some encoding of a molecule or something like this. But the point is that we have this unknown state, and we want to learn what the state actually is. So like, this is just some quantum system sitting, on a chip or in your lab, and you actually want the classical description of what the state actually is. And so the way we do that in quantum mechanics, the way we convert this quantum information into classical information is we'll perform some measurement on the state. This will produce some measurement outcome, and this will cause some disturbance to our state. Of course, with one measurement outcome, you can't deduce what the state of your system is. So you need to like repeat this again, perform measurements, get outcomes. You have to do this many times. Uh, you might also prepare multiple copies, 2 copies, 3 copies, many copies, and you might perform a measurement on all of these copies at once. This is often called an entangled measurement or a joint measurement because you have to your measurement creates entanglement across these copies. This, of course, does the same thing, produces measurement outcomes, and causes your state to collapse. And the idea is in state tomography is you want to take all of these measurement outcomes, do some classical post-processing, and write down the description of your state rho. So you're given access to copies of this n-qubit quantum state rho. And the goal is to produce this outcome classical description, rho hat, of rho that's close in some distance metric. And what distance metric that is could depend on your whatever application you have. Also, let me also say, feel free to interject at any point if you have questions or concerns, so on. But anyways, hopefully this is review. Okay, so we have our problem, quantum state tomography. I want to tell you guys a little bit about what is known. So I'm going to tell you about the copy complexity, the number of copies we need to consume in order to achieve our goal of outputting a description that's close to rho. So here's kind of a table of some relevant results. I'm going to turn your attention to this column with mixed states. This is like the general setting where rho can be a full rank mixed state. So you can see that like if we're allowed to perform these entangled measurements that I mentioned, in 2016 it was shown that 4 to the n roughly copies are necessary in order to recover our state in trace distance. Now, if we restrict the measurements allowed to single copy measurements, the copy complexity cost increases from 4 to the n to 8 to the n. And then there's an even further restriction we can make, and that's to single qubit measurements. So these are measurements that, are not even allowed to create entanglement across qubits within a single copy. So this is like a very restrictive form of measurement. And if you restrict to this type of measurement, the copy complexity cost increases to 10 to the n. Now, the problem we're going to think about in this talk is the special case where rho is assumed to be a pure state or promised to be a pure state. So this is like we're trying to solve this tomography problem, and we get to we're promised that rho is rank 1. And in this case, you can see that like you get no advantage between you get no advantage from using entangled measurements. So even if you use single copy measurements, you can achieve this optimal 2 to the n over epsilon squared scaling for trace distance. And the question that we kind of raise in our paper is, what about if we go even further? What if we only allow single qubit measurements? So like we're in this world where you could be trying to learn a very entangled pure state, and you're only allowed to perform single qubit measurements, creating no entanglement across qubits. And our main result is that at least up to logarithmic factors, so polynomial factors in n, but log factors in the Hilbert space dimension, you can achieve the same optimal copy complexity with this like very restrictive type of measurement. Um, any questions about this? Okay, so in this slide we talked about copy complexity, but you can also ask about running time. So just to highlight some previous work, GKKT18, they gave a single qubit pure state tomography algorithm that used like the suboptimal copy complexity of 3 to the n, and their running time was 8 to the n. And for single qubit pure state tomography, this was kind of the state of the art. And our work, in addition to like improving this copy complexity to the nearly optimal 2 to the n, we also have this nice this we also are able to achieve like nearly optimal running time. And in general, for like pure state tomography, so for state tomography in general, when it comes to running time, this is like the first work that achieves this nearly time optimal guarantee. And yeah, it has like this nice bonus that it's like also like the measurements are extremely simple. They're just random Pauli measurements. So that's just to kind of recap the main theorem that I'm gonna tell you guys about. Actually, by the way, is this window like in the way, or is that just
Which
on my
window?
screen? Okay, it
Uh,
might just be on my screen. Okay, okay, good. No,
No, I
that's
don't
what I
see.
wanted.
I don't see that. Yeah.
yeah,
Okay,
yeah. We
okay,
only see the slide.
beautiful. Okay, excellent. Okay. Okay, so yeah, just to recap what I said, we have an algorithm that solves this pure state tomography problem. It uses single qubit Pauli measurements, and this algorithm's nearly copy optimal, nearly time optimal, and it's not adaptive. And my goal for this talk is to just give you a high level picture of what this algorithm's doing. Like uh yeah, I guess Jello suggested keeping things intuitive and high level. So I'm gonna like spare like maybe like the less interesting calculations and things. But of course, feel free to ask questions as we go. Cool. So
I
the
just want to ask, like, so I mean, nearly is hardly like a technical term, right? So by nearly,
good.
you mean like up to logarithmic factors, is that right?
Exactly. I just mean I just mean this tilde here.
Okay.
Uh just yeah, by nearly I mean that we achieved the optimal scaling up to log factors.
Mhm.
Yeah. Cool. To start off, I'm going to tell you guys about how we can map any n-qubit state to a binary tree. So at the root of this tree, we have our input state psi. For concreteness, let's just think about this as a 3-qubit state. And this is the first level of our tree where we just have the root. And its two children are going to be these states psi 0 and psi 1. And the subscript 0, all I mean by this is like I'm going to introduce some notation here. This like psi sub x is just the state psi conditioned on the first qubits being in the state x. So psi0 is psi conditioned on the first qubit being 0. Psi1 is psi conditioned on the first qubit being 1. And we think of this second level of the tree, we think of these as 2-qubit states. We're ignoring the qubit we conditioned on. And
Can
then
I just
we do this.
clarify? Sorry,
Yes.
by condition, do you mean project on the first qubit onto X and then renormalize, or?
Yes.
Yeah, okay.
Yeah. So yeah, like measure the first qubit and post-select on the states that you see 0. Yeah, exactly. Good. And okay, then we do the same thing for these children. This is the same conditioning on the first 2 qubits being 0, 0, 0, 1, 1, 0, 1, 1. And in this third level, these are all 1-qubit states. And of course, you can do this for an n-qubit state. You'll just have a deeper tree. So the idea behind our algorithm is like a classic one. We just do divide and conquer. So we have our input state, which we can think of as this tree, like the n-qubit state being at the root. And we have these two conditional states, psi0 and psi1, corresponding to these two subtrees. And like the really bird's eye view of our algorithm is, in step 1, we are going to learn psi0 and psi1, these two conditional states. And then in step 2, we're going to learn like the coherence across the two branches. We'll learn the right amplitudes that lets us like glue these two states together and describe the root node psi. So just in symbols, hopefully to make it a little bit more clear, we have our state psi. We can decompose it, in this way that matches our binary tree. And I'm saying that in step 1, we're going to learn these psi0 and psi1. And then in step 2, we're going to choose amplitudes alpha 0 and alpha 1 so that this glued together state is like a normalized pure state that describes psi. So good. So the first thing that I want to tell you is that this type of scheme actually works. In particular, like if you did learn estimates of psi0 and psi1, there are actually good choices of amplitudes that will like produce a good final estimate. So let me just say that a bit more technically now. I'm going to introduce this distance measure, d sub f. This is the Frobenius distance between two pure states, psi and phi. And we have our input state psi that kind of decomposes in this natural way. And suppose that we're at the point in our algorithm where we have estimates of psi0 hat and psi0 1 hat. Also, apologies, in some of my slides, the hat's getting cut off, but these small like accent marks are supposed to be hats. But anyways, so you have psi0 hat, psi1 hat, and suppose we're able to like recover them to accuracy like root A0 and root A1. The question is like, do there actually exist good amplitudes that causes the Frobenius distance of our glued together estimate and the true state to be small? So here psi star is like the state you get here by like choosing these two amplitudes. And so the kind of the first lemma I want to tell you is that yes, these amplitudes do exist. There is a choice of alpha 0 star, alpha 1 star, such that this glued together state psi star is close in Frobenius distance to psi. It's depends on like P0 A0 plus P1 A1, where A0 and A1 are the accuracy achieved by our estimates of psi0 and psi1, and P0 and P1 are like the probabilities of observing 0 and 1 respectively on this first qubit.
Sorry, can I just ask a question about this? You're talking about existence here, which is confusing me a little bit. Like, is this really existence, or are you talking about whether there's an algorithm for doing this in a efficient way?
I'm just talking about existence. Like you could imagine, that the structure of the algorithm that I'm proposing just like doesn't work for some reason.
Because the estimates, the hatted psi0 and psi1 are maybe like away from the actual psi0 and psi1 in such a way that the coefficients don't exist. Is that what's happening?
Yeah,
there?
yeah.
Okay.
Yeah, exactly. Yeah.
Okay.
So this is kind of like a proof of principle that like there is a target, and then later on I'm going to tell you about an algorithm that like tries to hit that target.
Okay, thank you.
Yeah, for sure. And just to like maybe to give some rough intuition, I want to like change the parameters here a little bit. So imagine that we like recover both of these branching states to like error root epsilon. And for simplicity, let's just like assume that the probability of seeing 0 and 1 are both 1/2. Then our lemma is just saying that, there are good amplitudes out there, such that if you like glue your state together with them, the overall error is at most root epsilon. So we don't have this like horrible like issue where errors compound in some horrible in some nasty way. Like that, you can successfully do this type of gluing together. So again, going back to this slide from a while ago, like this divide and conquer approach, our lemma is just saying that like, let's like kind of on a high level, let's recover psi0 and psi1 to this like epsilon accuracy. And our lemma tells us that that's kind of good enough to have a good estimate of psi, assuming we can find the right amplitudes. Okay, so at this point, I want to give you like give you the algorithm again, but slightly more specified. Not too much more, but slightly more, just like some pseudocode. So we have our state learn like we have our algorithm learn pure state. And the first thing it's going to do is it's just going to measure the first qubit in the standard basis like a bunch of times. And sometimes you'll see 0, sometimes you'll see 1, and you just kind of categorize them. You set them into buckets. One thing that's worth noting here is that like if the probability of seeing psi0 is much higher than seeing psi1, you'll end up generating many more copies of psi0 than psi1. That's exactly what you want. The state that you're more likely to see is the one you need more copies for because you need to learn it to like a finer accuracy. So this like measurement process kind of like lets you obliviously like generate the copies in the right way. Anyways, so the point is you measure the first qubit a bunch of times to generate copies. And then we have this recursive call in our algorithm. We're going to call our function learn pure state on psi0 with this new accuracy parameter like attenuated by the probability you see 0. Same for psi1. And then you find good coefficients, alpha 0 and alpha 1 hat, that approximate these good coefficients that are promised to exist by the last lemma I showed you. And then you just, write down this description and output it. That's and that's what the algorithm's doing. Let's see. So yes, okay. So I like for the rest of the talk, I kind of just want to fill in some of the missing details here. So the first thing I want to say is that like is to do this like kind of copy complexity analysis. So like in this recurrence relation I wrote down for our algorithm, this S of n epsilon is like the copy complexity of our algorithm. And it's equal to 2 times this like S again from our recursive calls in step 2 and 3, where we're calling the algorithm again on n-1 qubits. And then there is a copy cost to step 4, where we need to find our good coefficients. And we want it so that when we solve this recurrence relation, we achieve like the claimed copy complexity of like roughly 2 to the n over epsilon. And it's not too hard to see. So I guess the question is like, how good does step 4 need to be so that we achieve this copy complexity? And a second question is like, how accurate do our coefficients need to be? Like, how close to the true optimal coefficients do we need to get so that our final output is actually epsilon close to the input state? And so for this first question, in order for the copy complexity to be roughly 2 to the n over epsilon, it suffices for this find good coefficients step to also consume about 2 to the n over epsilon copies. And our choices of amplitudes, alpha 0 hat and alpha 1 hat, need to be like root epsilon over n close to the optimal choices. And I'm not going to show you these calculations. They're not too hard to do. But this is kind of the target that we need to hit for this whole proposed algorithm to work. These are like kind of the main missing pieces. Essentially like this step 4.
Sorry, can I just ask? I
Yes.
mean, it seems it's very much a basis dependent thing. Does any of this depend on the I guess like the P0 and the P1 errors could be like if you balance P0 and P1, you might get better performance or something like this. Is that
No, I don't think you'll get, so first of all, like if you did this, you could only hope to shave log factors because it's
right?
optimal up to log factors. And I don't think you could, that'll even, I don't think that'll do anything for you. Um, I think these factors end up just kind of not really mattering all that much. Like if P0 is like very, very, very small, you just don't need to learn it to like very high accuracy. And so it kind of just balance, it's like self-regulating in that way.
So it's completely basis independent. Like it wouldn't matter
Yeah.
which basis you chose to measure the first qubit in. You would.
Um, I guess you're asking like, so we're gonna do like it's the branching basis independent. Yeah, yeah, I think so. This branching step is basis independent. Like there's definitely, you can always choose a basis to balance these two things out, but that'll just be more of a convenience thing than something that would like give you resource savings.
Okay. Thank you.
Yeah, that's a good question. Okay, so let's see. So yeah, this is the algorithm. It's not too bad. It's like a simple recursive algorithm. I'm like hiding a lot of the complexity that lives inside of step 4. But that's what we're going to talk about now. Oh yeah. So I just wanted to recap. Okay, like where are we at? Like, we have this algorithm, and the output of this algorithm satisfies our desired like complexity. Like the Frobenius distance between our output and the input will be at most root epsilon, and that's kind of the same thing as learning in fidelity. And our algorithm will use the claimed copy complexity, what I claimed at the beginning of the talk, as long as we satisfy two things. In step 4, when we find good coefficients, we're only allowed to spend like 2 to the n over epsilon copies. And the coefficients that our algorithm chooses need to be like solid approximations to the optimal value. That's like kind of the state of play now. So if we can do these two things, we're happy and our algorithm works. So finding the good amplitudes, this is like the algorithmic part. So our goal now, in order to get this pure state tomography algorithm to work, we've kind of boiled it down to the following problem. We're given descriptions of two pure states, psi 0 hat, psi 1 hat, and we want to find these coefficients, alpha 0 hat, alpha 1 hat, that are root epsilon over n close to the optimal amplitudes, and we only want to consume roughly 2 to the n over epsilon copies of psi. So essentially what we're asking for is we want to optimize over this like two parameter space. So like think of d, this function d of alpha 0 and alpha 1. Think of this as like some function that we're optimizing in these two choices of amplitudes. And this is just going to be equal to the Frobenius distance between our input state psi and this glued together state. And we want to optimize this. We want to find choices of alpha hat, alpha 0 hat, and alpha 1 hat, so that this objective function is at most the optimal plus this like root epsilon over n loss. And yeah, this is the right thing. This square root should not be over the n, but it doesn't really matter too much. But yeah, this thing in the top left's a typo. Anyways, so yeah, we're trying to optimize this objective function and only incur this amount of loss. Now, the intuition about like how you do this, it's like actually not so bad. The intuition is that like this Frobenius distance for pure states, it's actually this function of the the fidelity between the pure states. So we have like the magnitude squared of like the inner product of these two vectors. And so this ends up just being something that depends on like the angle between the two vectors. It's like slightly, it's like ever so slightly more complicated than that because it's like there's two parameters we're optimizing over, but that's the rough intuition that like the optimization landscape of D is actually very, very nice. You can show that there's like already you're just optimizing over two scalars. So this is like not too bad. And then the function, because it's like has the sinusoidal, because it's essentially a sinusoid, there's like a unique global minima. And because there's a unique global minima, if you can learn, if you can evaluate this function D at a few different points, you can actually just deduce the like D on every value, and in particular, you can just find where the minima is. So yeah, so like yeah, if you have some like sinusoidal type thing, it's not too hard to find the minima by just evaluating at a few points. So this problem of optimizing your objective function in these two parameters, we're able to reduce it to the problem of evaluating the objective function at several different fixed sets of parameters. So the task now is this evaluation problem. So we have these fixed inputs now, psi 0 hat, psi 1 hat, alpha 0 hat, alpha 1 hat, and our goal is to output an estimate, d hat, that is equal to our objective plus or minus some square root epsilon over n loss. So we want to basically approximately evaluate our objective function, and that will be enough for us to optimize over it. And of course, we have this requirement that in order to do this, we only want to consume like 2 to the n over epsilon copies of psi. Now, here's the thing. I know there's a lot floating around, but like recall now that this objective function is actually, we set it equal to the Frobenius distance between two states. So another way of like saying this problem that's like much cleaner, this problem of evaluating our objective function, is just like imagine we have two n-qubit states, rho and sigma, and we want to estimate their Frobenius distance to like accuracy gamma. And and we're allowed to use 2 to the n over gamma squared copies, because when we plug in square root of epsilon, we'll get our like desired epsilon copy consumption. So if we have an algorithm for estimating the Frobenius distance between two states, we can use that to evaluate this objective function d, which will let us optimize and then find the right coefficients. So our target is zoning in now on this problem. And it turns out this has been studied actually. Flamia and Liu solved this problem with 2 to the n over gamma to the 4 copies. And they also use Pauli measurements. And kind of one of the more technical contributions of our paper is to just give a totally new algorithm that achieves this desired complexity 2 to the n over gamma squared. Cool. So Frobenius distance estimation, that's like what we've boiled this all down to. So we have like two states, psi and phi, and our goal is to estimate their Frobenius distance. And so technically, if like I don't expect you to be tracking these details, but if you're really tracking this carefully, technically in the pure state tomography algorithm, we have copies of psi, and we have a classical description of phi, and we're trying to estimate the Frobenius distance between the two. But it's okay to just think of this as having copies of both because we can simulate copy access if we have the description. So just to keep things simple, just imagine the scenario where we just have copies of both, and we want to estimate the Frobenius distance. So the first thing that we are going to do is we're just going to take the rank 1 density matrices of our states and write them out in the Pauli basis. So each of these states they're kind of characterized by these coefficients WP and UP. And then if you plug these Pauli expansions into the Frobenius distance and kind of just do the arithmetic, you'll see that this the Frobenius distance is actually equal to this expression here. It depends on this like difference squared, but the average of the difference squared of these like Pauli coefficients. So, okay, I'm just gonna as we go, I'm gonna record like the pertinent information. So our goal is to estimate this quantity, this difference squared. And yeah, and it kind of depends on these Pauli coefficients of our states. Oh, sorry about that. Okay, so sorry about that. Okay. So the first, I'm going to mention a couple of claims. The first one is that for any Pauli P, one copy of psi suffices to draw from a random variable whose expectation is WP. Yeah, so this is actually not complicated. All you do is you just take psi and project it onto the ±1 eigenspace of P. You'll get a Rademacher random variable whose expectation is WP. And the same thing is true for phi, of course. Okay, so that means that with a copy of psi and a copy of phi, we can draw from a random variable whose expectation is like WP, 1/2 WP minus 1/2 UP. And what we do is we just use this first claim to draw from each random variable separately, and then we just like perform this, we just like take the difference of the two. And okay, so that means that if you have two pairs of psi and phi, so 4 copies in total, you can draw from a random variable whose expectation is their difference squared. And right, so you just you this middle line, you just run this procedure twice and take the product of the two, and scale by 4. But anyways, does this make sense? That we can use like 4 copies and draw once from this random variable. So, good. So unfortunately, our work is not done. The estimation algorithm that we have is a bit non-trivial, and it's kind of because while we can't, for a fixed Pauli, while we can get this like difference squared, we have to estimate the average over all Paulis. And so I want you to imagine like two very different regimes. On the left-hand side, imagine we have a situation where these like differences squared are 0 for like almost all of the polys. And for a small number of them, they're non-zero and roughly equal. And then on the other end of the spectrum, imagine that like all of the polys have a non-zero difference squared. But because they're all non-zero, of course, they're all very, very, very small, like exponent, like super small. And depending on which regime we're in, our strategy, the way we're going to use our copies of psi and phi needs to change. So in particular, on the left-hand side, we want to, what we want is, we want to sample many, many polys and only use a few copies per poly. And that's because most of the time we're going to sample polys with like, that have, where the like the differences of the coefficient squared is 0, and we're going to get no information really. And so we want to sample many of them to increase our chances of hitting one of these non-zero ones. And then we'll use a much smaller number of shots in order to like get some signal from these. And that's okay because these are actually quite large. Now, in this other regime where like all of the polys are non-zero, but they're very, very, very small, our strategy is going to change. Now we're going to sample fewer polys because we're going to be hitting non-zero ones all the time, but we need to use many shots per poly because this difference squared is so small. We need a much finer a much finer accuracy to actually like get a good estimate. And a priori, when we're doing this Frobenius distance estimation, we don't really know which regime we're living in. And so that's like the main non-trivial that's like the main hurdle that we need to jump when like designing this algorithm. So the rough idea is that we design an estimator that can kind of capture every regime and kind of combine the information. So I'm not going to go into too much detail on this, but I just want to give you some sense. So the idea is that we break the possible weights of these different squared into levels. Like the jth level corresponds to having the difference squared be roughly 2 to the minus j. And then for each of these levels, we'll budget our copies in a way that makes sense. So we'll choose the number of polys we sample and the accuracy per poly in a way that makes sense for that level. So if we're on the left-hand side, we'll do few shots per poly, many polys. If we're on the right-hand side, we'll do many shots per poly, but fewer polys. And for the levels in between, we'll kind of like interpolate between these two strategies. And then for each of these levels, we'll recover some estimate, and then we have some way to just combine these together. And this ends up giving us our Frobenius distance estimation. So just to tie this all together, we kind of just went down a deep rabbit hole. We have this algorithm, this recursive algorithm for learning pure states. And all of that time that we just spent, like the real technical part of this paper is in finding these good amplitudes that glue our state together. And we essentially reduced this problem down to the task of doing Frobenius distance estimation. And we use that estimator to optimize for the right choice of alpha 0 hat and alpha 1 hat. And okay, yeah, so that's pretty much it. And I also made a claim about like how this algorithm is like linear time in the Hilbert space up to log factors. And I'm just going to defer that to the paper. The details are all there. There's some like careful choices of data structures and things that get you this. And yeah, just yeah, leave that to the paper. So anyways, I want to wrap up with some, I know I'm slightly over time, but I want to wrap up with some future directions. Just two kind of broad things here. or actually one broad thing, one specific thing. So the first thing is like just to encourage everyone to think about single qubit measurements. They're kind of surprisingly powerful. At least so far it seems that way. So I just told you about this paper where we show for pure state tomography, there's no major cost in restricting to single qubit measurements. And then Megal and William had this earlier paper with Ryan O'Donnell where they study state certification, and they also have very nice results where they show that like single qubits actually can like kind of effectively solve a version of the state certification problem. So just more generally, it's yeah. What else can single qubit measurements do? Then the last, the only other question I'll pose is whether our algorithm can be made truly optimal. So what that would mean is, we would want an algorithm that consumes this many copies. So here, delta is like a confidence parameter. We want our algorithm to succeed with probability at least 1 minus delta. And epsilon is the error parameter. We want our algorithm to recover in infidelity. And what we achieved in this talk is shown here on the left. So we have this tilde hiding these these n factors, and our log is multiplicative instead of additive. So depending on your taste, you might not care about this at all. Like the left-hand side might just be good enough for you, but I will say there is a conceptual question here too. Like the question is asking, like, is there any cost whatsoever to restricting to single qubit measurements? Like maybe it is the case that you have to pay a logarithmic overhead if you're going to use these single qubit measurements, or maybe we're in this world where actually you get everything you want. You can actually get this like this optimal scaling. And an answer to the second question, it's like very specific, but it actually informs us about the first question, about like what kind of power should we be expecting from single qubit measurements. But anyways, okay, that's everything I had. Thank you so much for listening. Feel free to email me if you want to chat more about this. But yeah, that's everything. Thank you.
Right. Thank you very much for very informative and illuminating talk. Yeah, I guess we actually have like a bunch of time, like maybe for discussions and comments and questions. So if you have some, feel free to do it now.
I have a bit of an out there question. So when you're trying to do this Frobenius norm estimation, I mean, because you know phi, could you, I have a strategy and I'm just wondering if you've looked at this. Could you try to like find the unitary that turns phi into the all zero state and then implement the inverse onto psi and then use now you're in the right basis and you can do Frobenius norm estimation in that basis and it should be much simpler? Have you guys looked at that?
Well, so okay, I guess we were trying like one of like the main things about our algorithm is that it's single qubit measurements. And like not only is it single qubit, it's just Pauli X, Y, and Z measurements. So it's like as simple as it gets.
Right.
As soon as you get into this business of like applying unitaries, that unitary is a part of your measurement. And that's like
Yeah, fair enough.
for phi, that's gonna just like entangle everything. It's probably gonna be like very deep circuit and so on. So we did think about things like this, and then we would go, oh shoot, like that, like
Yeah.
that's not single qubit. Yeah, yeah.
Okay, great.
Right. Any other questions here? Maybe I can ask something. So when you said like, so there will be like certain regimes, and then you can divide into levels. So how do you know how many levels you need, or in some sense it doesn't matter?
So you kind of split the levels up into the like based off of this like exponential like you have a good yeah. So you split the levels of you're trying to capture things with magnitude like roughly 2 to the minus j at the jth level. After like log many levels, uh like that 2 to the minus j is just going to be, you can just truncate. Like yeah, you're going to be in a regime where that like 2 to the minus j is so small that you can just think of it as 0. And that happens when you're like inside of the error. Like if you're trying to recover to like accuracy plus or minus gamma, once 2 to the minus j is on the order of gamma, there's like no signal to be found there. You can just think of it as 0. Does that make sense?
So I guess like whatever like you were trying to do, like your measurements would tell you sort of where you can cut off. Something.
Yeah, actually, even the input to your algorithm is like, I only want to recover this to accuracy like 1/10. That is what tells you how fine your levels need to go.
Mm.
Yeah, yeah. So like the input to the algorithm will tell you when to stop.
I have one more question. In your recursion formula, you had this like plus W function.
Yeah.
And you kind of in the presentation you said, well, what do we need the W to be to get the thing we want? And then showed that you can achieve that. But what if W was smaller than that? Would your scaling be faster? Or is the first part already gonna kind of ensure that you get it to the n on epsilon squared?
The first part will give you this like 2 to the n over epsilon.
Right. So you wouldn't get any saving by
scaling.
reducing W.
Yeah, but if you wanted to get rid of the log factors, those are inside of the W.
I
Yeah.
see.
Yeah, yeah. But yeah, like just by like this, yeah, because you're like this recursion is just splitting by factors of 2, and the depth of your tree is like n, that's where you end up getting like 2 to the n roughly. And yeah, we have a lower bound. So if you're beating 2 to the n over epsilon, like you definitely made a mistake somewhere, I guess. Yeah.
Epsilon squared, is it?
Yeah, okay. I kind of was trying to brush this under the rug a little bit, but like it's 2 to the n over epsilon for fidelity, and 2 to the n over epsilon squared for trace distance. Uh, for pure states, this difference doesn't really matter. Like they're like the cost is the same.
Great, thanks.
Yeah, yeah, for sure.
Right. Let's see. There's somebody else. See anyone? I do have like a few short questions, like 2 of them maybe. For the first one, so I guess like because there's been some recent results where you can use pure state tomography methods to extend it to mixed state by using this kind of like purification approach, like random purification channel things. I don't know if
Yeah.
you have looked at this. I guess like this would naturally be applied to your case as well. Does it?
Yes. Okay. So so there's this like paper like reducing mixed state tomography to pure state tomography. Um, if you plug our algorithm into that framework, you end up with uh a copy optimal mixed state tomography algorithm, where the first part runs this random purification channel, and the second part runs our algorithm. And it's kind of nice because all of the entangling operations happen in this random purification channel. And then when you run our algorithm, it's all single qubit measurements. So it kind of it has this nice separation where all of the entangling operations, and there's a lot, those happen up front, and then our algorithm's all like single qubit. But yeah, that's a good point. We mentioned that in the paper that you can do this.
Yeah. Okay. And then maybe like the last thing I wanted to ask, like, so this is for qubits, but like if I had like, let's say qubits or higher dimensional things, I feel like the structure still kind of applies. I don't know what is the actual dependence on qubits here.
Yeah. Yeah, I guess I think something I think something very similar will work. But instead of having a binary tree, the number of children you have will be like the qubit
Oh,
dimension.
okay, I see.
So you like if you have q trits, you'll have like 3 children, and yeah, all that, like yeah, this I'm like pretty confident that this all works out. And if your like qubit dimension is q, you'd have something that like scales like q to the n.
But your amplitude distances will scale with d as well, right? So you could
Yeah, that
potentially
yeah. So
get
yeah,
some extra
Uh,
factors.
oh yeah.
yeah. Maybe that's worth the figuring out, yeah.
Hmm.
But yeah, for sure, at least a high level structure, I think you just want the number of children to increase, and you have to like go through, and I guess like the hairiest part is this like the gluing step, like figuring out how that updates. But my guess is that this would all work out.
So can I just ask if you were like running your algorithm on what happened to be a product state, you get no improvement at all, is that right?
Yeah. Wait, like let me think for a second.
Like just the computational basis state.
Yeah, exactly. Yeah. If uh okay, if it's a computational basis state, your recursion tree will actually just be like a line graph. But
Yeah, but you got to
but
learn that
you're
it's a line graph, right?
well, when you measure the first qubit, you'll just see like 1 or 0 every time. I think what you could do is you could have a product state of, like, let's say you have a product state of all pluses, right? Like then you're in this balance world where saying 0 and 1 is 50-50.
No, I specifically want the computational basis state because I'm kind of still trying to get at this thing of like, is this really basis independent? I'm very surprised because like if you magically knew the right basis to rotate so that it's like a product,
Mhm.
then can you learn it faster or um
Um,
like say it was all plus state, but somehow computational basis is better for you, then you could do Hadamard's and then learn it.
yeah,
I'm just trying. Yeah.
that's true. Yeah. No, it's like certainly true that if you know a basis in which your state is very sparse, like it's only supported on a small number of basis states, uh you should be able to like upgrade the algorithm to like exploit this. And we like in the way we've presented this, we don't do that. Uh and like yeah, thinking about like a yeah, I think like for us, the state changes what the recursion tree looks like. So we're splitting on 0 and 1. So if it's a computational basis state, our recursion tree is actually will be simple. It'll just be we'll always either go all left or all right. But if it's the all plus state, our recursion tree will be ridiculous, right? Like we're going to be branching 50-50 at every node. We're going to build this recursion tree with like 2 to the n nodes, and it's all to learn the product of all pluses, which is like a trivial state, right? Um, so like certainly if you're trying to exploit this type of structure, you can, if you want to assume something like this, uh, you could. The thing that you would have to do, I think that you're getting at is like you need some algorithm that learns the right basis to simplify it.
Yeah, but
And
I mean,
that change of basis might be complicated.
yeah, I guess
Yeah.
here's what I was hoping for. Like, I was hoping first of all that this statement is more robust than just like either it's completely sparse or not. So like, what if it's close to a product state? Like the branches are like low probability. Like if A, like the amplitude A is more extremal, does it help? So one is hoping that it does, and two is like you could imagine a very kind of brute force-ish algorithm where you just do a bunch of local unitaries and then check which one gives you the more kind of peaked amplitude, and then kind of go down that path. And so you're doing
Right.
these local rotation each time, trying to uh, I don't know,
Yeah.
extremify your basis.
Yeah. Yeah. Okay. I'm not. I don't have a total answer to your question, but like, there's two different things that I want to I want to highlight as different. Like, one is like having this product state structure. Uh, if you're trying to find like unitaries that take you to this product state structure, in general, that's going to involve like entangling qubits, or like disentangling qubits, I should say. So you're not going to have a single qubit algorithm this way, but it's totally a viable approach. If you like, there's no reason we need to fix ourselves to single qubits. The other thing is like that I mentioned was like having sparse support. So you're not a product state necessarily, but you're only supported on a small number of states on that basis. Like, uh, that is something more along the lines of what our algorithm could exploit while still using single qubit measurements. And you can do that by kind of like terminating the recursion early, like in clever ways, I think. We didn't write any of that down, but I feel like you should be able to do that. But yeah, all that to say, like, your hope of like maybe getting improvements, maybe shaving log factors and stuff, like maybe I can't say one way or the other whether this would work out or not. My guess is that it wouldn't, but I'm definitely not sure.
Yeah, I guess it seems like if
Yeah.
it does help, it's not for many states at all. So it's a very small fraction of states.
Right.
Yeah. Okay.
Yeah. And yeah, that's the thing. Like, yeah, maybe people have applications where this structure exists and it's worth it, but like, I'm too far removed from those types of discussions to know.
Thank you.